take a look at the second part of 11.2 dealing with the chi-squared test. The last test that we want to talk about with chi-squared is called the chi-squared test of independence. And basically what makes this one different than the homogeneity problem is the homogeneity one is taking a look at multiple populations. Here we're just going to take a look at a problem where we are looking at a single population, and basically we want to take a look or analyze the relationship between the two variables that are being compared. And we're trying to see, are they independent of each other, or is there a relationship? And if there seems, or if they're not independent, is that relationship statistically significant? So we're going to take you just through a couple quick examples on how to do that, and we'll be done. So these notes probably won't be super long. All right, so to do that, in this first example, I'm actually referring back to something we did back in Chapter 5. Chapter 5, we were taking a look at the relationship between gender and whether or not you had allergies. So we collected some data from 40 students. And back in Chapter 5, we concluded that the events female and allergies were not independent for members of this particular sample. So what we want to do is just show you and relive again why this is the case. So as I pull this up here, what you would do is, if you remember conditional probabilities, if they were independent, the probability of having allergies given they're female should equal the probability of having allergies given they're male. So being male or female, these probabilities should not impact having allergies. It should be the same probability. So that's what you'll see here. Then having allergies and gender would be independent events. So over here in blue, what we did was we calculated, well, what's the probability of being female here and having allergies? 10 out of 23 was 0.435. Male and having allergies was 0.471. So since these two probabilities are not equal to each other, they're not independent events. So now that we see that they're not independent, the question is it statistically significant? Does being male, as we can actually start to see here, does it have a tendency of do males have a tendency of having a higher probability of having allergies than females? Is this actual difference in the probability statistically significant? So to start to analyze it, just like we did before, it says we're going to make a well-labeled graph that compares the conditional distributions. Okay, so one of the things that we could do is take a look at the differences in males and females. So you can see I just did, again, another segmented bar graph. Pretty easy to do. Lots of times for these types of problems, they don't necessarily have you graph them. It's more the homogeneity ones. I can see them do those. But nonetheless, here it gives us a visual representation. We can see that males have a higher tendency of having allergies than females, according to at least our sample. So basically, that's what I'm just noting here. Suggests males tend to have allergies more than female. Might suggest there's an association between gender and allergies. So this is what we want to analyze. This is what we want to find out. So here's the nice thing. If we go to do this test, on the next page, you still have the four-step process. Basically, the only thing that really changes is the type of test. So what you'd want to say is you're doing a chi-squared test for association or independence. Okay? So in the null hypothesis, that will change. You're going to, instead of saying there's a difference between the groups, you're going to say there's no association between the two categorical variables. We're going to say there's either no association, or you could say they're independent. Okay? Given we know they're not truly independent because there's a difference, we just want to see, is it a real significant association or not independent between the two categorical variables? But here's the cool part. After that, the plan, other than stating that it's a chi-squared test for association and independence, all the conditions are the same. When calculating out, you still do the expected counts just like we did before, so that you can get each individual chi-squared statistic and sum those all up. Your degrees of freedom is exactly the same. Row total minus 1 times column total minus 1, so that's exactly the same. And you use your chi-squared CDF function. Okay, so again, chi-squared CDF on your calculator in the same area where you're going your chi-squared statistic to 999 degrees of freedom. All right, once you get that, compare it to your significance level, 5, and we're going to either reject or fail to reject to see if we actually do have an association going on. So let's take a look then at the allergy problem and just kind of run through the 4-step process with it. Then we'll do one more example, and that will be it for these notes. So these notes go somewhat, hopefully, quickly. Whoops. I apologize, I hit the wrong button there. I need to advance the page. All right, so here we go. So we want to write the null and alternative hypothesis with this data here. So as you can see, my null hypothesis simply says there's no association between gender and having allergies, while my alternative is I suspect there is. So there is an association between gender and having allergies. Again, remember when doing significance tests, we're hoping to show statistical evidence so that we can conclude the alternative. Okay? So we're trying to see, is there actually an association, or at least is it statistically significant? All right, so our test, chi-squared test for association. Right? I tend to use association. You can use independence, but I tend to like to say the word association at the 5% significance level. So, simple random sample of 40 US students. Yep. The next part, large sample sizes. So I went through and already did all the expected counts. So I did 23 times 18 divided by 40 to get my first one. 23 times 22 divided by 40 to get the next one. So I did all of those ahead of time. Likewise, when I check the independence, since we are sampling without replacement, 10 times our sample, there's at least 400 students we could have surveyed to check on this situation. Okay. So now we have our expected counts, we have our observed accounts, so observed minus expected squared divided by expected. This one I could actually write out all of the terms. Okay. So observed minus expected squared divided by expected. Do all 4 of those. My degrees of freedom, 2 minus 1, 2 minus 1, which is only 1. So my chi-squared statistic actually is pretty darn small here, 0.051. Okay? So my p-value, chi-squared CDF, lower bound to infinity, degrees of freedom of 1. Okay? Remember, since this is a degrees of freedom of 1, this chi-squared doesn't start at 0. It's actually like that inverse power model. So you can see that this one is, the likelihood of getting a sample like this is pretty high, 82.1%. Kind of what we would almost hope. It'd be kind of interesting to see if allergies was associated to gender. So in our case, this is our result. So our result, or one more extreme, would occur 82% of the time if our null hypothesis was true, if there was no association between the two. Since it's greater than 5%, we are rejecting the null hypothesis. That is, we do not have statistical evidence that having allergies is associated with gender, which is which would have been interesting if it actually was. All right, so I know I kind of flew through that one. My guess is you might have had to pause. I am going to move on to the next one. So if you're not finished with this one, I'd definitely pause. And then we'll go to the second one. All right, last example. Kind of like this one. You kind of think about this at when you were a kid in, elementary school kid, at least in school. It says, we want to know whether boys or girls get into trouble more often in school. Below is the table documenting the frequency of boys and girls who got in trouble in school. So boys, girls, we have the table, whether they got in trouble or not in trouble, and the total. So it says, based on our sample results, perform a test to see if we have evidence at 5% significance level that getting into trouble at school is associated with gender. this one there might be an association. We'll check it out. All right, so null and alternative hypothesis again. The null would say there is no association with getting into trouble in school and gender, while the alternative would say there is an association between getting in trouble at school and one's gender. So do boys get in trouble more often than girls? Looking at the data, there is definitely more boys than girls getting in trouble, and there is more girls, so my guess is at least it's showing that more boys. The question is it statistically significant? All right, so let's check it out. Chi-squared test for association, again at 5% since it told me a 5% significance level. We do have a simple random sample of 237 students. I need to do my expected counts, so if you trust my table calculations here, all right, so I did row times column total divided by table total. So again, just to let you know on that, 83 times 117 divided by 237 gives me the value in the spot for 46, which was 40.97. So I'd expect to get just under 41 boys who got in trouble. I got 46. I would expect 42 girls getting into trouble. I got 37. So we're going to check, is those differences statistically significant? We are sampling without replacement. Check to see if the population is greater than 10 times the sample. We're going to assume there's at least 2,370 students that we could have sampled here. Definitely the case since, we're not just, it didn't necessarily say at one school. We could be sampling from many schools across the metro area. So only 4, so I actually write all of the fractions out. So observed minus expected squared divided by expected. So I do each and every single one of these. Again, I think I showed you in the last video, you can do list 1 minus list 2 squared divided by list 2 and let your calculator do a lot of the work for you. Okay? I would highly encourage you to do that. Degrees of freedom here again is just 1. My chi-squared statistic, a little bit bigger, 1.886. Okay? So if I enter in chi-squared CDF, 1.886 to infinity, 1, I do get a p-value of 0.17. So our result, or one more extreme, is happening here about 17% of the time if there was no association between getting into trouble at school and gender. Okay? So because that is still greater than 5%, okay, we do fail to reject our null hypothesis, meaning we do not have statistical evidence that there is an association between gender and getting into trouble at school. So even though more boys were getting into trouble than girls, it was not statistically significant in this particular case. All right, so that ends the notes for actually all of chapter 11. So we've covered all 3 tests now. Goodness of fit, chi-squared test for homogeneity, and this last one here was on association and independence. All right, have a great day.